we are recording, and from current slide, we'll pick up from here. Let me do say this. I thought of it while that was coming up. Just reminding everybody, this class still, I think I've gotten the 6th paper in now, so we're up to 6 out of 19, so we've still got twice as many who haven't turned in a paper as those who have, more than that, in fact. Quiz 1, we've made progress on that. We're still missing 1, 2. 2 people haven't turned in quiz 1. Of course, I'm preaching to the choir here. Well, not quite. Yeah. Okay, and then test 1. If you don't see your grade on Blackboard, that means I couldn't tell if you're finished from the test or not. So we've got 9 have turned in the test. So not quite half the test. Test 1 are finished, at least from what I can tell. If you are finished, your grade's not there, let me know and I'll post the grade that I have there. All right, any questions? We're on page 132, very end of, well, we're in chapter 2, polynomial rational functions, the very end of 2.2, which is polynomial functions of higher degree. So here we have one. Use the intermediate value theorem to approximate the real zero, and they say real zero is if there's only one of them, of f of x equal x cubed. Now, I have a question for you. Do you agree with them that this even could have a real zero? Yay or nay? Is it possible that there's no real zeros for this one? Yeah. Leading term test. What does that tell you? What's that? Yes. Okay, and what does that tell you? Opposite directions, right? Negative toward negative, positive toward positive, right? What does that tell you? It's a polynomial function. What 2 features does that have? Jazz? Smooth and continuous. So if it's a continuous function, starting somewhere way down there, going somewhere way up here, guess what? Has to cross the 0 somewhere. Now, it could cross it how many times? Up to 3 times. We don't know if it will, but it's got to cross it at least once because of our end behavior. Very good. So we know there is a real 0. We don't know where, though. So that's what we're going to pursue. How would you start? Okay, how do you factor that? Okay, let's see how that works. I think I'm learning something today. Okay, and factor out an x squared. What do you have left? Now what? Nice little exercise, but doesn't get you anywhere. This is not factorable, unfortunately. Most cubics are not. I mean, I don't want to say that. A lot of cubics are not factorable. In fact, I think I'll erase all the ink on the slide. Okay. So, if it's not factorable, what might we try? Okay. She likes graphing. That's good to know. I'll try to put more of those on the test. Okay. No. What do we do? Hint. What do they say? Use the intermediate value theorem. Now, I know it was a long time ago that we talked about it, Thursday. Okay? So, how does that go anyway? Basically, the intermediate values theorem says if we have a f value, a y value here for one value of x, here's our x. have another value here for another value of x, then in between those two values, there's x somewhere between these two x's that every point in there has to be hit at least once, right? So the key is to find two values for x, one of which the f is positive and one of which the f is negative, and then guess what? You're guaranteed, okay, Alexis? Okay. You're guaranteed that there has to be a zero between those. So what we start off with is just finding, trying some x's and find out if we can find a plus and a minus on our f of x. So what's the easiest x to choose? 0, I like it. Okay, so let's first do f of 0. And what does that give us? 1. All right. You want to go right or left? From 0. Left. So to negative. Okay. So you want to try f of negative 1. What would that be? Okay, that would be a minus 1 plus 1. What does that give us? A negative 1. Ding, 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 ding. We found a value 0 where it's positive, negative 1 where it's negative. That means what for us? There's got to be a 0 for the function. F has got to be 0 somewhere in between negative 1 and 0. You want to pick a value? Negative 1/2. Why not? So f of, now I bet you y'all are going to use calculators, right? If you don't, you can do it by hand, but you can either do negative 1/2 or negative 0.5. I'm going to do negative 1/2 because I don't have a calculator. Poor me. Okay, that would be negative 1/8 minus 1/4 plus 1. Well, negative 1/8, you want to get them all in terms of eighths? Well, negative 5/8. I mean positive 5/8. 5/8. Okay, because you have negative 3/8 plus 8/8. That would be, yeah. Okay, so what does that tell you? Is between what and what? Negative 1/2 and negative 1, because here it's positive, there it's negative. So you want to try another one. We'll try Terrell, see if he's here. Yes, he is. Okay. All right. So what you want to choose between negative 1/2 and negative 1? Negative 3/4. Let's try it. F of negative 3/4. Okay. What's negative 3/4 cubed? Negative 27 eighths. Right? Minus. Oh, that's not right. No, so wrong. Okay, I was doing 2, not 4. Negative 27/64. I believe that's right. 4 cubed. 4 squared is 16. 4 times 16, 64. Isn't it? Brain's not working today. Yeah. Okay. And next. Negative 3 squared, 9/16 plus 1. All right, I think this time we need to get everything in 64ths. So it'll be negative 27/64 minus we need this to be a 64, so we have to multiply by 4. 36 64ths plus 64 64ths. What does that give you? Negative what? Negative 63 64ths? Woo! So we got a 1/64. Yeah, that's close enough to 0 for me, I think. Okay. I think if we've done it right, we're awfully close to negative 0.75. Okay? It has to be just a tad short of that because you still have to know greater than that. So I would try using a calculator, negative 0.76. So if someone has a calculator, do that. F of negative 0.76. We know it's got to be closer to -1 because it's still slightly positive here and negative here. So let's go a little bit closer with a calculator. What do you get? Yeah. Do negative 0.76 cubed minus 0.76 squared plus 1. Negative 0.17. Okay? And punch in for me and see what 1/64 is. I should know it, but 0.1/64. Nathan's here. He can give us the answer. Huh? No. 1/64. No. Say again. Just 1/64. Yeah. Say again. 0.156. So that's actually closer to 0 than the 0.76. So I would then maybe do 0.75 negative 0.751 and see what you can keep playing with it and see. This is awfully close. Okay, awfully close. See what that one gives us. What's that? We call it the method of exhaustion. When you get tired, say, that's close enough. Okay. No, usually what you do, you determine ahead of time how many decimal points you want of accuracy. If you want it within 2 decimal points, 0.75 I think will be fine. Negative 0.75. But if you want it within 3, then you keep going until you get within 3. See, this is within nearest 10th of being that. So if you want, you decide. What do you get with negative? 0.0124. That didn't change a lot, did it? So yeah. So you can keep going. I would be, I'm not going to, or not even have you do it. Negative 0.752, or maybe jump up to 753. You choose and keep going and see how close you can get this to 0. Okay? And like you say, stop when you get tired and say, I think that's close enough. Okay? Or Orion's here 1. Okay. So, let's see how the method we did. You find a place where the F is positive or it's negative. Pick something in between on X. Try again. Keep going between the positive and the negative. And keep narrowing it down until you get close enough for government work and say that I'm happy with that. Something near 0.7. Now it would be negative 0.751. Okay? If you tried another one and you got closer, go for that. Okay? All right, let's see how they did it. We're going to erase all this ink and see what they did. Begin by computing a few function values as follows. And they started with -2, silly them. That was a hard number to do. That gave you -11. -1 gave you -1. We found that. 0 gave us 1. Well, then why even mess with 1? You got the 2 is somewhere between -1 and 0. Okay? Once you have that, pick a value in between there. Because f of -1 is negative, but f of 0 is positive, you can apply the intermediate value theorem to conclude the function has a real 0 somewhere between -1 and 0. Okay? Well, to pinpoint it more closely, divide the interval into tenths and evaluate the function at each point. Yeah, I want to do that. You could have done it that way. I think it's better to pick a midpoint, and then if one's close, and don't go midpoint, just go a little bit, usually had a little bit, And this gave us between -0.8 and -0.7. Negative here, positive there, so we know it's in between there. We got there in 2 steps. We didn't have to do 10 steps, which is what they did to get it. We did it in 2 steps and got closer than they did. Okay? They go again. F must have a real 0 between -0.8 and -0.7. And then they drew the graph, which makes Amber happy. And that gave them -1, 1, 0, 1, positive 1, 1. And sure enough, 1, 0 here. Notice here it was dipping down again. And we didn't do enough points to tell this, but it was dipping down, but then moved back up. It didn't dip down low enough to cut it 2 more times. See, if this has been a deep cut, then it could have had 3 zeros. And that's all you could have had. Our end behavior said you're going this way and that way. And since you found 2 places where it was both 1, and you know it wasn't a straight line there, it had to be, and you don't know the dip that occurred right there, but it had to have a dip somewhere in there. Okay? And all you have to do is pick some more points and fix your graph. So we got closer than they did, quite a bit closer. We got 0.751. They only did between -0.8 and 0.7. That was close enough for them, so they were happy with it. Guess what? I'm not even sure if that's about -0.5, that's about 0.75. Yeah, you're somewhere in there. Okay. So you can't get much closer on the graph anyway, so that was good enough. Make sense? Okay. So you can do it. If you have a graphing calculator, it'll find it for you. Okay? Get to know it. Okay. But if you don't have that, you can still get pretty close. Might be a good idea to go home or library or another classroom or somewhere and do the checkpoint as soon as you can, just so you can play around with it and see if you can find the real 0. Okay. That finishes 2.2. Let's do vocabulary. Quite a few of these. The graphs of all polynomial functions are blank, which means that the graphs have no breaks, no holes, no gaps. What does that mean? Continuous. Got it. Number 2. The blank, blank, blank is used to determine the left-hand and right-hand behavior of the graph of a polynomial function. They call it leading coefficient test. I call it leading term test, whichever you choose. Okay? I think leading term covers it better than leading coefficient, but that's just me. Number 3. A polynomial function of degree n has at most blank real zeros. A polynomial of degree n has at most blank real zeros, n real zeros, and at most blank turning points. Yeah, n minus 1. Very good. Justin's here. Even better. Okay. All right. Now, as you see, this one, 3rd degree polynomial, it could have up to 3 zeros. It only had 1, but it still has 1, 2, just barely 2 turning points. Yeah, can't have any more than that. That means it's not going to head up that way and then come down again and have another 0 somewhere there. No, It can only have at most two turning points. If we found them, it's going to keep on going up, keep on going down. Guaranteed. Okay. Number 4. When x is equal to a is a 0 of a polynomial function f, the following 3 statements are also true. The first of these, x equal a is a blank of the polynomial equation f of x equals 0. Yeah, a 0 or a solution or a root, any of those would work. Number B, blank is a factor of the polynomial f of x. Blank is a factor of the polynomial f of x. Say again? X what? X minus a. Perfect. Okay, sorry, my hearing's so bad. That would be a factor. Okay, number C. A0 is an blank of the graph of f. Intercept. Yes, an x-intercept of the graph of f. Very good. Number 5. When a real 0 of a polynomial function is of even multiplicity, the graph of f blank the x-axis at x equal a. Touches. Does not cross, but touches. Okay? And when it is of odd multiplicity, the graph of f crosses the x-axis at x equal a. Very good. Number 6. A factor x minus a to the kth power, anytime k is greater than 1, yields a blank blank x equal a. Say again? Anyone have an idea? Repeated 0, repeated root. Exactly. Okay? X equal a of blank k. The word is in the previous number 5. What do we call k then? Yes. The word is in question number 5, or vocabulary question number 5. That big long word has a blank k. If k is that exponent, raised to that many powers, that x equal a is of big long word in number 5. Multiplicity of k. Exactly. That's what k is called, the multiplicity. All right, number 7. A polynomial function is written in blank form when its terms are written in descending order of exponents from left to right. Standard form. Now that is higher order polynomials. Your standard form for a quadratic, you know how that looks. We already did that in the previous section. Okay, number 8. The blank-blank theorem states that if f is a polynomial function such that f of a is not equal to f of b, then in the interval a to b, f takes on every value between f of a and f of b. Intermediate value theorem. Very good. Oh, I thought it was up here, but it isn't. It was on the previous. Okay. Homework exercises here. I think I've assigned them before. I would do all of 9 through 14, but the answers for 9, the odds are in the back. 9 through 13 are in the back. But do them all. They're fun. They exercise you. Okay? Then, do either 15 or 17 or both. Any of the odds between 19 and 29. Do either 31 or 33 or both. Any of the odds 35 to 49. Either 51 or 53 or both. Any of the odds 55 through 63. 65 through 73. 75 through 87. And either 89 or 91 or both. do either 93 or 95 or both. That's the ones we did today. And then try to do some of the odds from 97 to 103. Okay? Those are applied problems. If you have trouble with any of those, bring them to class and ask. We will do those. Exploration, they've got quite a few true false here. You don't expect to see many of these on the test, but still thinking through those is a good exercise. So I would do some of the odds 105 to 111, and then think through any of the odds 113 through 117. You don't have to do a lot about them, but just sort of make sure you understand what they're talking about. Any questions? Did I not go over this? Okay. For more accurate approximation, I guess I didn't. Compute the function values between f of negative 0.8 and negative 0.7. Okay? We did that. We did negative 0.75. And we applied it again. And then we went between these two. So we didn't do negative 0.8, but we went there. By continuing the process, you can approximate the zero to any desired accuracy. If you want it in one decimal place, we had that in just a couple steps. If we had it on it within 2, probably would have taken us another step or 2. Within 3, we'd have been working for a while. But actually, they zoom in pretty quickly. So you decide how accurate you want it and go for it. All right, that does finish 2.2. Let's move on to 2.3. Now, I think you've had most of this before, okay, 2.3. If you haven't, it's not that hard, but let me know if this is all brand new to you. Polynomial and synthetic division. Now, what that means is polynomial division and then synthetic division. Have y'all ever done polynomial division? I figured you had. How about synthetic division? Yes, I thought probably you had. Was that in a course here or in high school? Both. Okay. All right. So this will be pretty much a review, hopefully, for everybody. Use long division. Yeah, I know. I'm thinking this is 100. Yeah, you had it in 100. I know you did. Right, Nathan, right? Okay. Yeah. All right. Use long division to divide. He was in my class. I knew he had it. Use long division to divide polynomials by other polynomials. We're going to do that first. And then, for only certain kinds of division, we can use what we call synthetic division. Much quicker, but it only works for certain ones. Polynomials of the form this, x minus k. When you're dividing by that. We'll talk about that. And we'll then do the remainder theorem and the factor theorem. They both tell us important pieces of information, and we'll be using those repeatedly in what comes next. Okay? Did you get that? Okay. Got it? Okay. So let's start with long division of polynomials. Okay. Suppose you're given a graph of this function. F of x is equal to 6x cubed minus 19x squared plus 16x minus 4. And notice that it looks like you have a 0 here at 2. Now, we don't know that for sure, but it sure looks awfully close to 2. Yeah, it looks like you have either 1 or 2 more zeros here, but they're fractions, and we can't tell what they are. Okay? So, if this graph sort of leads you to think you might have a 0 at 2, then if 2, 0 is an x-intercept, tell me 3 other things that means about 2. 2 is a 0 of, if you set this polynomial equal to 0, 2 will be a 0. Very good. And we're going to focus on that. Give me the other 2, by the way. How about x minus 2? that be called? A factor. That would be a factor of this polynomial. There is a big key right there. Okay? And the last one, what was that? Say again? No, okay, yeah, no, we're not worried about shit. That's so complicated. Okay, so, whatever the other one is. Notice that a 0 occurs at x equal 2, and at least we think it does, and here's how we tell. If a 0 occurs at x equal 2, that means x minus 2 is a factor of f of x, and there's some other factor out here that multiplies that to give you this. So then we use division. Now we're going to do it first in long division, and that's what example 1 is going to do. But before we do that, I want to do a little exercise with you to see if you even remember long division. I'm going to make up a number. I've got to get my pen recolored. Okay. Maybe 12 divided into 6,19164. Okay, can we do that? Not with a calculator. Okay? How do we do long division? Tell me what you do first. 12 will go into 61. Now notice here, long division, or division in general, usually starts from the left and works its way right. Adding, subtracting, multiplying, you start from the right and work your way left. So division, kind of backwards, okay? So 12 will go into 61 how many times? 5. Now what do you do next? You multiply. 5 times 12 is 60. And then what do you do? Subtract. And then what do you do? Bring down. Okay, you got it? You divide, you multiply, you subtract, you bring down. Divide, multiply, subtract, bring. Okay, keep going. Will 12 go into 19? How many times? 1 time. Then what do you do? Multiply, and that gives you 12. And then you subtract, that gives you 7. Then you bring down a 1. Will 12 go into 71? 5 times. 5 times. Then what do you do next? Multiply, and that gives you 60. And then you subtract, that gives you 11. Time out just a moment here. What if that had come out 13? Then you go back and increase that by 1. Because your remainder here when you subtract can never exceed your divisor. If it does, go back and add another number there. Yeah, remember that. Okay? Next, bring down a 6. Nine times, and then you do what? Multiply, and that gives you. Okay, and then you subtract, that gives you 8. That's less than 12, okay. Bring down the 4. 7 times, and that gives you 84. No remainder. What does that mean? That 12 is a factor of this. 12 times this equals that. It factors into that exactly. If you had had a remainder here, 2, 7, anything else, then that wouldn't have gone into there a whole number of times. It wouldn't have been a factor, right? All right, y'all remember that really well, okay? So, let's do away with all that and see if we can do long division of polynomials. What do you think we put on the outside? X minus 2. What do you put on the inside? Yeah, 6x cubed minus 19x squared plus 16x minus 4. And what do you think you do first? Yeah, start on the left and work your way right, just like we did. And we'll start with this. X will go into 6x cubed. How many times? Second? 6x squared times. Does everybody see that? Okay, basically what you do, coefficient into coefficient, 1 will go to 6, 6, and then variable x will go into x cubed, x squared times, right? Okay. This book does. And if you like doing that, go for it, okay? It really doesn't matter. When you're doing long division, you have to keep that straight. But here, I have no preference one way or another. I'm going to sometimes have to write a remainder up there, so I want to leave as much room as possible. It really doesn't matter. But yeah, you could put this over this if you want to. Okay? The thing I like about this is that I'm multiplying this by this to give me this. So I'm staying on top. But it doesn't matter. Either way you prefer. The book does it the way Jonathan said. So what do we do next? Multiply. 6x squared times x would be 6x cubed, but we also have to multiply the other part, and that would be minus 12x squared. These you got to put under the ones that are the same. Now, what do we do next? Subtract. Okay, now, because now we're dealing with signed numbers, I like to use the rules for signed numbers. And do you remember what subtracting signed numbers, how you do that? Change signs and add. That way, you don't get real confused. Okay, I'm a minus 19 minus a minus 12. That's something, you know. Just take care, change signs and add. So make this a minus, that a plus. Now add. That works, right? So what do you get here? 0. That's exactly what you want to get there. What do you have here? Say again? Negative 7x squared. You're adding, okay? And then what do we do next? Bring down the plus 16x. All right, next. Nope. Yeah, divide. X into negative 7x squared would be negative 7x times. And then what do we do? Multiply. Negative 7x times x is negative 7x squared. Negative 7x times negative 2 is plus 14x. Okay? And then you do what? Change signs and add. So that becomes a plus, and this one becomes a minus. Easier to do for me than it is for you, okay? All right, you add, that goes away. Fantastic. What happens here? 2x, and what do you do? Bring down the negative 4, and now what? Divide, okay? 2x, x will go into 2x, how many times? Plus 2 times. And then you multiply, and that gives you 2x minus 4. And guess what? No remainder. What does that tell you? That x plus minus 2 is a factor of that. That means x equal to was indeed a 0 for that polynomial. That's what it tells you. Okay? And that this is your other factor. Right? Now, we factored the polynomial. We haven't factored it completely. We divided, yes, but we haven't factored completely. The question remains, can this be factored any further? But guess what kind of polynomial that is? A quadratic, second degree. Let's see if we can factor that baby, okay? If it can be factored, what would be two possible, let's unfoil it, okay? What two possible factors could you have for 6x squared? There's a bunch of them. You choose two. You said 3x. You want to do 6 and 1, okay? Shame on you, okay? But we'll do it, okay? 1x times 6x, okay? Now, where do we look next? Sign of the last term. What is it? Positive. What does that tell you about these two signs? They've got to be the same. What's the sign in the middle? Negatives, that means they both got to be negative. Now, guess what? What's the only possible factorization for 2? 2 and 1, except we could do it in either order, so let's put a 2 here and a 1 there. Guess why I didn't want to put the 2 over here? Because then 2 would have been a factor here. You could have factored out a 2. And since you can't factor out a 2 here, we know 2 is not a factor. So if it's going to work, it's got to be the 2 going with the x and the 1 going with that. Well, let's see what we get there. Foil it and see what we get. 6x squared. That gave you the right answer. Yeah, we knew that would work. Next. Minus x minus 12x. Doesn't work. Okay? Wrong number. If you got the wrong number, change your numbers. And we can't change the 2 and the 1. Okay? They just change back and forth. So therefore, what are we going to change to? Yeah, 3 and a 2 up here. Okay? So let's do that. Oops. And which order? I better put the 3 here and the 2 there. Why? Because, again, you don't want to put the 2 with the 2. You factor out a 2. This doesn't have a factor of 2. So don't do that. Let's see if this works. It may not work, remember? Okay? Let's see if it does. 6x squared, we knew that was going to work. Then, minus 3x. Minus 4x, that's looking good. Plus 2. Yes, yes, yes. Ding, 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 we got it. Okay, 6x squared minus 7x plus 2. So now we factored it completely. So when you're doing these, you may have big, long, hairy polynomials of high degree. Chip away at them until you get down to quadratics. And then either factor. If it won't factor, what do we use? Quadratic formula. Exactly. We've done it. So what were our other 2 zeros? If those are factors, what are our other 2 zeros? I'm taking one more step. If you set this equal to 0, then what would you conclude here? 3x minus 2 equals 0, or 2x minus 1 is equal to 0. What does this give us? X equal, say again, 2 over 3, 2/3, and this would give us x equal 1/2. And remember our original graph? Remember those two were real close to each other? 1/2 and 2/3 aren't too far apart. That's 0.5 and 0.666666666. Okay. So yeah, those are pretty close. They were both positive. Remember, they were both between 0 and 1. Yes, this looks like we may have it. Both of those were between 0 and 1. One was pretty close to 1/2, and one was a little bit over 2/3. I can buy that, okay? That's using long division, right? Now, hang on to this for later, but notice we really didn't use this much to get that first number. We didn't use that much, and if we had subtracted here, which we would have, we got everything gave us a 0 there. So just remember, these things didn't really contribute a lot, not in the way we worked. So just hang on to that thought. Let's go on and clear here and see how they did it. Okay? Well, here's how they did. They put x minus 2 on the outside, and they put the polynomial on the inside, and then they started their division, and they did it like Jonathan did. Yeah, right, okay. X will go into 6x cubed, 6x squared. You divide first, then multiply 6x squared times x, 6x cubed, 6x squared times negative 2 is minus 12x squared. Then they subtract. I like to change signs and add. If you subtract sign numbers without any problem, go for it. But changing signs to add takes away the ambiguity, the chances for error. I'm always trying to minimize my chances for error. So I change signs and add. That gave you a minus 7x squared. Bring down the plus 16x. Then you divide again. x will go into negative 16x, negative 7x squared, negative 7x times. Then you multiply negative 7x times x is negative 7x squared. Negative 7x and negative 2 is plus 14. When you subtract here, these go away, and that gives you a 2x. Bring down the 4. X will go into 2x, 2 times, plus 2 times. 2 times x is 2x, 2 times negative 2 is negative 4. When you subtract here, you get a 0, which means this is a factor of that, a perfect factor. Therefore, this is a factor of that as well. But let's see now if we can, okay, I see what they're doing there. This is how you do your division, okay. Now the question is, can we factor that any further? We know we can. Well, we don't know if we can factor it, but we could apply the quadratic formula if we needed to. So from that division, you conclude that 6x, say again? Oh, okay. 6x cubed, this big thing here, is this factor times that factor. Exactly. Then by factoring this quadratic further, and we can do that by unfoiling, we get this 2x minus 1 times 3x minus 2, exactly like we got it. And they leave it like that. We went back and identified our zeros. Okay? So, in example 1, x minus 2 is a factor of that polynomial. You got that from graphing. We won't always graph, but you can do it. I know that Amber loves graphing, so she'll always graph. We'll find other ways to do it. The log division process produces a remainder of 0. That means you got it right. It was a factor. Often log division will produce a non-zero remainder. What does that tell you? That wasn't a factor. It wasn't a 0. Okay? But it also tells you something else. We'll get there later. For instance, when you divide this polynomial, which is a quadratic, by x plus 1, yeah, you can do it. Let's try it. X plus 1 will go into x squared plus 3x plus 5. X will go into x squared. X times. I wish they hadn't done this. I like us to do it, and they didn't leave us, but we'll do it. Okay. X times x is x squared. X times 1 is x. And then what do you do next? Subtract. These go out. And 3x minus x is 2x. Bring down the 5. X will go into 2x plus 2 times. 2 times x is 2x. 2 times 1 is 2. You do have a remainder. That means this is not a factor of that. Yeah, we could all do that. But it's not a factor, because you do have a remainder. So, remainders are bad things? Not really. Okay? I want to show you what that remainder tells you, but we'll do that later. Got to resist temptation of jumping ahead. So, what if we're writing that answer in a fractional form? We say the dividend divided by the divisor is equal to the quotient, what we had on top, plus remainder over divisor. We did that, remember, in long division. You had a remainder, put it over your divisor, that's your fractional form, right? You did that. Same thing here. Here's another way to write it. This also applies, what if you multiply every term here by your divisor? That x squared plus 3x plus 5 is equal to x plus 2 times x plus 1 plus, and then multiply this by that, the divisors go out plus 3. And that's what we used to do too. When you're checking your long division, you multiplied your quotient by your divisor, and then added the remainder to get the dividend. And sure enough, you did. This illustrates the theorem called the division algorithm. Either this form or that form, perfectly okay. When you're doing these long divisions of polynomials, you can write your answer either like this or like that. Okay? Here's the division algorithm. If f of x, that's going to be our dividend, and d of x, our divisor, see they both start with d, so have f of x be the big one. d of x being the divisor of polynomials, as long as this d of x is not 0. Why not? You can never divide by 0, okay? Ever, okay? Then the degree, okay, now here's the other key. If you're trying to divide this into that, this has got to be a lower degree than f. Not even the same degree, has to be lower. The degree of d of x has to be less than or even equal to the degree of f of x. If the divisor is greater degree than the dividend, you can't divide. You just can't do it, okay? But if you can, then there exist unique polynomials, q of x, that's going to be your quotient, and r of x, that's going to be your remainder, such that the f of x, the original function, is equal to your divisor times your quotient plus your remainder. That's how we used to do it in grade school. We still can do it that way. Okay? Or the other way to write this is f of x divided by d of x is equal to q of x plus r of x over d of x. Either way. For r of x, if that r of x is equal to 0, that means that's a perfect factorization of your function. Or, and here's the other thing. Remember, we said that before too. This remainder in log division of numbers, the remainder always had to be less than the divisor, right? Here, the remainder has to be a lower degree than the divisor. Or the degree of r of x is less than the degree of d of x. So it doesn't have to be a lower number because you got functions here, it has to be a lower degree. If the remainder r of x is 0, d of x divides evenly into f of x. Those two are factors of f of x. Make sense? All right. Here's the other way you can write it. Like I said before, the dividend divided by the divisor is equal to the quotient plus the remainder of the divisor. And you see the degree of the remainder must be less than the degree of the divisor. The degree of the dividend must be greater than or equal to the degree of the divisor. All right, in the division algorithm, the rational expression f of x over d of x, this is what we're going to do in section 6, is improper. F of x over d of x is improper. Now, for improper fractions, what does that mean? Give me an example of an improper fraction. 11 over 3. The numerator is greater than the denominator. That's improper. You can divide them and get a mixed number. Okay? Well, what we mean with functions being improper is that the degree of the numerator is greater than or even equal to the degree of the denominator. That would make it improper. Okay? Because the degree of f of x is greater than or even equal to d of x, the degree of d of x. On the other hand, how many hands do you have? The rational expression r of x over d of x, and I just said that earlier, has got to be a proper rational expression because the degree of r of x has to be less, not even equal to, less than the degree of d of x. Okay? Make sense? So, before you apply the division algorithm, follow these steps. Very, very important. First, make sure your dividend and your divisor are in decreasing powers of your variable. If you got them all mixed up, you're going to have a really mixed up answer. Probably totally wrong. So always be sure they're in descending order, not ascending order, descending order. Number 2, this is also important. If you're missing an exponent, like you have an x to the 4th and then an x squared, you have to put in what they call placeholders with 0 coefficients for the missing powers of the variable. Got to do that. Otherwise, you're going to get, things won't line up, you won't have things to multiply and subtract properly. Be sure you have every term accounted for. If you're missing any terms, put a 0x cubed or whatever in there for that. Okay. They're skipping examples 2 and 3. Want to go back and do 2 and 3? Sure we do. All right. Goodness gracious, they don't give us much space. So we'll do it on the synthetic division thing. All right, let's divide this one. Divide x cubed minus 1 by x minus 1. What do we put where? X minus 1 outside the house, knocking on the door, and what goes inside? X cubed. Oh, very good. Plus 0x squared. See, he noticed we're missing some degrees, some powers. Have to put a 0. Okay, what's next? Plus 0x, missing another one. Minus 1. Very good. Now what? Divide. X will go into x cubed. X squared times. You can scoot it over there if you wanted to. Okay? Then you multiply, and that gives you x cubed minus x squared. You see why you got to have a placeholder there? If you had written the minus 1 there, you couldn't. Everything would have been messed up. Okay? So then what do we do next? Change signs and add, and that gives us x squared. Then what? Bring down nothing. Okay? Bring down 0x, 0x. And then what? Divide. X will go into x squared plus x times. Then you do what? Multiply. X squared minus x. See, you need that 0x holder there. Then what? Change signs and add. These go out. What are you left with? X minus 1. And then what? Are you through? Wait, is that your remainder? How do you know it's not? Degree of this is equal to the degree of that. Can't happen. It has to be less than the degree of that. So we keep trucking. And what do we do? X will go into x how many times? Plus 1 times. And then multiply. 1 times x is x. 1 times minus 1 is minus 1. 0 remainder. What does that tell you? X minus 1 is a factor of x cubed minus 1. But we knew that already, didn't we? Difference of 2 perfect cubes. You remember that, didn't you? Yes. X minus 1 times x squared plus x plus 1. Much easier to do the division, I think. Even easier when we learn how to do synthetic division. Okay. So sure enough, that factors exactly. Okay? By the way, there's checkpoints after every one of these examples. And you know what I forgot to bring up with me? I left my watch somewhere on Saturday, so over the weekend, so I've got to go back and get it. And I don't have a clock. How are we doing? 9:09. Okay, good. We've got plenty of time. Okay, let's try example 3. Any questions on example 2? Okay. Let's try. Oh, you're still writing? Okay. No. You have time to get it. Sort of get in a rush at the end because I know Nathan doesn't like to leave until I get as much information as possible. All right. Got it? Okay. So let's erase this ink and let's do example 3. Divide negative 5x squared minus 2 plus 3x plus 2x to the 4th plus 4x cubed by 2x minus 3 plus x squared. How do you do that? Say again? Yes, we definitely are going to rewrite both of those babies. What's going to go where? Yeah. The quadratic is going to go outside the house. So that's, and say again how you rewrote it. X squared plus 2x minus 3. That goes outside the house. Inside the house is 2x to the fourth plus 4x cubed minus 5x squared plus 3x minus 2. Okay. Now what I usually do is count down. 2, 1, 0. 4, 3, 2, 1, 0. Yeah, count down your exponents. Make sure that tells you two things. You got them in the right order and you don't have any missing. Okay? If you skip the number, then put in a 0. If you don't have the right order, fix the order. Okay. Where do we begin? X squared will go into 2x fourth. How many times? 2x squared times. You could move it down over there if you wanted to. Fine, I don't care. Next, multiply. 2x to the fourth, fantastic. Plus 4x cubed minus 6x squared. Everybody agree? Now what? Change signs and add. Minus, plus, and that middle one becomes a minus 2. I have to erase it. Okay. All right. I can add those two. And guess what? Those also go out. That's not always going to be the case. In fact, most of the time it won't. Then what do you have left? X squared. And then do what? Bring down a plus 3x. And since we got 3 terms here, let's also bring down your minus 2. You got that because you wiped out 2 terms here. Now what? Divide, yeah. How do you know you need to divide one more? The degrees are the same. Keep going until the degree of your remainder is less. And what was that? X squared and x squared plus 1 times x squared plus 2x minus 3, and then you what? Change signs and add. So again, let me wipe out the minus or the plus, make it a minus. And this gives you a 0. This now gives you a x second plus 1, right? You're adding now, okay? That's what makes it easier in my book, is a heading. X plus 1. Is that a legitimate remainder? Can you have a variable in the remainder? Sure you can. It's a function of x. Do you know it's a legitimate because this degree is less than that degree. So sure you can have that. So you could write your answer, quotient this, remainder that. You could do that. You could write it in any other form. They wrote it in the division type form. The previous one they wrote in the multiplication type form. Either way you want to do it. Okay? There is a checkpoint there. I would definitely do it. So how are we doing now? Say again? Oh, no. It can't be over. All right. So where do we pick up next time? I guess we pick up right there, synthetic division. Okay? Homework exercises here. Okay? You can do number 7, everybody. Do number 9, everybody. Then you can try any of the odds 11 through 25 and stop there because we haven't done synthetic division yet. All right, now, have a question for you. I wasn't sure, I didn't think we were going to finish this section today, but we did come relatively close. I've got the quizzes ready. If you take them today, that doesn't shorten the time you have to work on them. So if you want to take them, you certainly can. Anyone want to go and take the quiz today? Okay. just so you can get started on it. Again, officially you don't have it yet, but you can pretend you don't. Okay. All right. And I'll also have a question for you. And that question will be, do you need graph paper? Oh, guess what? They always have graphs, right? I think only one. Okay, I think I'm down to it now. Nope. Okay. So, get rid of some of this. Okay. Okay. You want to grab it? Okay. Paper. Yeah, this is take-home quiz. No, you have to do it in the next half a second. Okay, no. You want to take one? Okay. You grab paper. You grab paper? You want it? You grab paper? Yep. Okay. You grab paper? You grab paper? Remember, the clock hasn't started on this yet. So you grab paper? You grab paper? All right. You grab paper? You grab paper or yeah, big one back. What are you doing taking two quiz? Huh? Did you grab paper or quiz? Sure, okay. Yeah, I got more here. You not quiz. Don't take two. Okay. You just need. Oh, you got that. You're trying to confuse me, aren't you? You got that. Okay. Sure. Absolutely. You got that? What's that? Okay, right now? You don't want to do that? Okay. Okay. You want to go next door? You have started, right? Yes, sir. Okay. Any of the rest of you finishing the test? Yeah, just hanging around. Yeah, I am. You are? Okay. So let me find those. All right, good deal. All right. Well, and okay. I hope I've got everything in order. All right, you can either come through here or go around. Okay. I'm sorry? Okay, take your time. No one else is here for the next class yet.